Hello and welcome to today's webinar on how to design predictable PCB interconnects using systematic sink or stream approach. My name is Marko Marin and I'm Signal Integrity Engineer working at Infinera Metro Hardware in Stockholm, Sweden. And the other presenter is Dr. Yuri Shlepnev, who is the president and the founder of Symbian, where he develops Symbian electromagnetic signal integrity software. So the background material for this webinar today, it has been presented at the DesignCon 2018 in February this year, and also at the IEEE EMC Symposium in July this year. Today we will focus on key elements of the work we did. All the technical details and complete reports with analysis to measurement correlation is available on Symbian webpage in the App Notes section. So let's begin. So outline for today's webinar. It's a brief introduction, description of systematic sink or stream validation process, EVR1 test board design. EVR stands for expectation versus reality. That's how we named our validation board. I'm going to speak about the measurements and generalized model parameters extraction. We'll come to board cross-sectioning. From there, Yuri will speak about material identification using GMS parameters, validation, conclusions, and some things we found what happened above 30 gigahertz. So why is interconnects so unpredictable for 28 to 56 gigabit signals? Well, if you think about it, most of the tools on the market, they claim that they are correlates and they are valid for designing of interconnects for bit rates up to 28 or 32 gigabits per second. Yet they don't show any proof. I mean, how do we know that they correlate? Also, the boards as designed in layout tools is not the same board that we get back from manufacturing. There are some geometry adjustments and things that we don't have fully control over. Also for measurements, making measurements from basically from DC up to 40, 50 gigahertz is extremely difficult, both in aspects of not all instruments are suitable for this task. You have to find really good phase stable cables, connectors, etc. So it's a really daunting task. So what can we do instead? Well, we can make predictable interconnects. So here we have a design success fire triangle. So if we focus on these three elements, we come closer to have a systematic approach for predictability of PCB interconnects. And first of those, if we begin with the modeling, accuracy of the EDA tools must be systematically validated. And that must be done in a systematic base, not just for a few test strips, but rather on a whole broad range of interconnects as usually found on production boards. Material models and manufacture adjustments, they need to be identified. PCBs are not manufactured as designed. Here, the biggest lack is lack of material models. Usually, we only get from manufacturer values for the DK and DF at certain frequency points and just no information about the type of copper foil, but no useful data that we can use for simulation. And also measurements. We're going to see how we can do things in measurements so that we can trust more our results. And in this case, predictable, it means analysis will correlate with measurement. And key elements for this is modeling, measurement, and manufacturing. And systematic validation is the key to success. So, what is systematic validation process? Usually, the purpose of building validation boards is manifold. It can be used to pre-qualify the PCB manufacturer or type of new laminates you're planning to use on your next production board. You can do it to benchmark your EDA tools. And you can also use it to learn more about high frequency measurement in the microwave to millimeter wave range. So how does the validation process begin? Well, first of all, we select materials and define PCB stack up with a manufacturer. And we specify the prepregs, cores, copper foils, agree on the trace widths, via hole designs. We exactly specify which drill hole sizes we want to use for the vias, which pad sizes, etc. And we always keep the manufacturer in the loop, so they can guarantee that they can manufacture this. Next step is design of test structures with a simple EM analysis. And this can be used using datasheet values when designing reflective structures such as the vias or the launches. Third point is manufacture the board. After the manufacturing, mount the connectors. In our case, we used solderless compression mount connectors, 2.92 millimeters that go up to 40 gigahertz, or 2.4 millimeters that go up to 50 gigahertz. We measure the S parameters using time domain network analyzers or vector network analyzers. We validate the quality of the measurements according to IEEE T370 metrics. Lately has come out metrics from IEEE that define what are good practices for making measurements, and these can be validated in Symbior. After we are satisfied with the measurements, we cross-section the board and we identify the manufacturing adjustments to see have the manufacturer's expectations on how the trace width is going to be actually correspond to reality. Step number 6, we identify broadband dielectric and conductor roughness models with generalized model S parameters or SPP light techniques. And finally, number 7, we simulate all structures with identified or validated material models and confirm adjustments consistently and compare S parameters and TDR with the measurements. Here is the important thing that we have one set of test structures on the board that we use for material identification. Then we should have another test of structures that we use for validations, and those structures should be typical structures as found on production boards. Via holes, AC coupling caps, meander traces, traces with different widths to see if our models are consistent across the wide range of interconnects that we might find on actual boards. So here's our validation board. The stack up for our validation board, it's basically same stack up as used on the production board, and also the board is manufactured using same IPC class quality control as the actual production board. The game by doing this is that we can pre-qualify the manufacturer. Can they build boards as we're going to use on the production boards using same laminates, same drill hole sizes? And from here we can also learn more about the laminates. We can extract the material models that will help us close analysis to measurement correlation later for actual production boards. So looking at this, the only thing that we have gotten from the manufacturer on the left is the stack up. This is the pressed stack up. So this is the estimated thickness of the final board in all layers. We have got DK and DF values at 1 gigahertz, and we have also got information that we are using HVLP copper. And that's basically all. This is the best we can do. Later, we're going to see how far we can get with just datasheet values. So this is the validation board design. Traces in red are used for material identification. Validation board contains traces on the bottom, inner 1, inner 3, and inner 4. And we assume that the inner 4 and 5 have same properties because we could not put all these traces on the board. Board also contains other connectors for evaluation. traces that are marked with black, those are used for validation of the material models and to see how well can we go with our geometry adjustments. So the most important thing we have found is the launch. Launch is used to transition the signals from coaxial cables to the strip line traces or the microstrip traces. So it's most critical part of the validation project. And its design will limit how accurate will the material extraction be. The most important thing to consider when designing the launch is that it should be lowly reflective and not sensitive to manufacturing variations. You're going to see this later. So in our case, the launch was designed for connectors 2.92 millimeters or 2.4 millimeters. We have put 9 stitching vias. They connect all the ground planes. We have specified the drill hole diameter and the pad size for the signal via and the ground vias. And we estimate that this launch, by its design, that is the distance between the signal via and the stitching via, when the frequency comes close to the quarter wavelength, it's probably going to lose localization. But we have plenty of stitching vias, and we expect the return path to remain low. And this launch is optimized without the connector. It's also important to notice that if we want to push beyond the 30 or 40 gigahertz, we should probably include a connector also in this model. So the post layout observations. The PCB is manufactured with impedance control. The reason for that is when we spoke with the manufacturer, they said, well, according to IPC, you have tolerances on the core and pre-preg and on the trace width. So basically, it turned out that they felt most confident if they could allow trace width and spacing adjustments. They could not change the dielectric, nor the pre-pregs. Those were fixed. So basically, they could change the trace width and the spacing. And we have no information on the trace shape. We have no reliable information on the solder mask, neither how thick is the solder mask, nor its electrical properties. No information on the conductor roughness model, besides that we are using HVLP copper foil, and no information on the actual back drilling. There are some launches that are back drilled on this board. So basically, I said everything from 6 to 15 mil is the variation for the stub. All of this makes pre-layout analysis inaccurate and practically useless if you are targeting 30 or 40 gigahertz. Measurements and general product extractions. Well, when we were doing measurements on this board, it was really challenging. The board in the beginning was designed for a time domain network analyzer. Measurements with time domain network analyzer were pretty noisy, about 10 gigahertz, which could not make our material extraction pretty reliable. So we had to switch for different options. And we tried 3 different brands of network analyzers. Actually, this board was used also for evaluation of network analyzers. So we got one from Anritsu, from Rode Schwarz, and from Keysight. And all of them had, in one way or another, some issues. The one that we proceed to do measurements with had a pretty good performance, but it had some low frequency problems. And the reason for that is, another thing, the demo unit we got to borrow was supplied with really thick cables. So we need to find a new cable. So this part took the longest in the project to make the measurements. The measurements for the 50 gigahertz VNA, it showed pretty good. It was a good measurement. However, we saw using Symbior that something is wrong at really low frequency. So looking at the return loss, the return loss goes up. and this is not what we expect. We expect return loss to flatten out and go to some value. So this was caused by the electronic calibration kit. All three vendors told that when it comes to calibration of vector network analyzers, the most accurate method for calibration is using electronic calibration. In the case with the Keysight PNA, the electronic calibration kit has built-in DC blocking caps. And this is used in case we are measuring active devices. So if you have some DC bias across the cables, you can actually damage the calibration kit. So they put DC block caps, but this compromises the accuracy of the source matching in 10 to 50 megahertz region. So your reflection coefficient is really inaccurate in this low region, and this makes extrapolation down to DC really, you cannot trust it. And we need this in order to get a DC point. Yes, and also this caused some passivity problem at the lowest frequencies. So the S parameters were non-passive, non-causal at the lowest frequencies, which makes it strange. I mean, usually you think it's the highest frequencies that are difficult, but not. So making a broadband frequency measurement from DC up to 40, 50 gigahertz is really challenging, even for these high-end VNAs that cost hundreds of thousands of dollars. So one possible correction we did was to switch the calibration kit and use mechanical calibration kit. But problem with that one was it only went to 26.5 or 7 gigahertz. So we couldn't go so far in the frequency. So one way we did was we cut the data below 75 megahertz, and we did extrapolation with rational function fit down to the DC. And actually, the DC point is very important. There's a nice app note from Aritsu about what happens if you inject small errors below 10 megahertz. It can basically take an open eye and make it fully closed. So low frequencies matter as much as high frequencies. So with the low frequency data, we identified the copper resistivity. According to earlier studies, we found that the resistivity of the copper is slightly higher than of the bulk copper. And this also is reported in other reports a couple of years ago back from Intel, and also in Paul Huray's book. There's explanation why does this happen. So the TDR and general S parameters for the microstrip traces. This was done with the TDR, and TDR that we see here is obtained from the S parameters that were measured up to 50 gigahertz. And we can see there's around 3 ohm variation in the launch and along the traces. And also on the right side, here we see the generalized module S parameter. Basically, a generalized module S parameter is obtained, in this case, by subtracting 4-inch trace with a 2-inch trace in a special way, so that this length difference between them, it's matched to its characteristic impedance at every frequency point, which makes this line or trace segment refractionless. So it represents only pure insertion loss, and this is used later for material identification, or you can use this if you want to exactly know how much attenuation does the traces contribute to. And in this case, we see up to 30 gigahertz, we have got really good generalized module S parameter. And also we can see that we have the phase delay difference in the common and the even mode. In the even and odd mode, and this we expect this will cause far end crosstalk in the microstrips. For the strip line trace, we see that we have a capacitive launch, but it's pretty much consistent. So important thing when designing these traces for generalized model S parameters is that the launches should be the same on the short and on the long trace. We see around 2 ohms variation along the trace. Maybe it's some probably due to homogeneity between under the traces. We have the glass fiber and the epoxy. And also here we can see that we have a slight difference in phase delay between the even and odd mode. So this indicates that the medium in the strip lines, it's not homogeneous. We will have a slightly far end crosstalk. So now is the part when we cross-section the board. So, well, it was quite surprised when we cross-sectioned the board. This manufacturer actually came really close to what they promised they would. I mean, looking at the strips, we were expecting 108 micrometers. In practice, they got 108.8 on this one, and 111 on this one. And also the spacing was pretty much close. So they did a really good job. And also the traces are perfectly rectangular. This would make the pre-layout analysis accurate if we had the material models. However, for the microstrip traces, the situation was different. Traces were much narrower, about 10 micrometers. Also, they were more thicker. Plus, we can see that this region between the traces, the solder mask is really thick, while it's really thin on the actual traces. All of this makes analysis for the microstrip much more difficult. So we need, in practice, we need to cross-section the board to identify the adjustments for the microstrip trace. When it comes to the launches, here also we see that everything on the board moves. So there's no need in spending endless hours in optimizing launches, because it's never going to be like that on the actual board. Rather, you should spend time on making your launch not sensitive to manufacturing variations. Here we can see, for example, that the drill hole, it's slightly larger. It's around 260 micrometers. Also, we can see the offset in the anti-pads. So the structure is a bit off, but still it performed pretty good using the just datasheet values. Roughness. Well, even though we specified HVLP copper, once the board, when it's being done at the PCB manufacturer place, they change the roughness of the traces. They do micro etching, oxidation. So same copper foil will end up being different at a different PCB manufacturer. This makes analysis just with the values obtained for HVL copper inaccurate, because it's going to be different for each PCB manufacturer. Each has its own special treatment for increasing the adhesion to the pre-preg. And this data cannot be used to define the roughness models. Unfortunately, we have to make the boards, measure them, and cut them up. So here are the final adjustments for the validation process. Thickness of pre-pregs is reduced by 3 or 5 micrometers. And for core, it's the same as we expected. The microstrip, as we shown earlier, there were some adjustments, and also some slight adjustments on the strip lines. And basically, this is it. Now we do the material identification part and the validation part.
Sorry, I was on mute. At this point, we were getting some results already in form of measured data, GMS parameters, extracted reflectionless scattering parameters, and we've got adjustment of the geometry. So we can try how models built with those data, available data, will match the reality. And obviously, the first experiment was not really good. So right here, you can see insertion loss measured, compared with insertion loss computed for reflectionless case, so no reflections in the transmission lines, and phase delay on the right axis. This is for strip line, and this is for micro strip line. In both cases, we are considerably off with losses, insertion loss. So the phase delay is scale is very large, so it's not maybe a big deal, but insertion loss is definitely a problem. So obviously this is expected because of we didn't have anything to put for the conductor roughness model to be able to model a conductor roughness. So anything we would put in there would be pure guess. It would be kind of completely unscientific approach. So, to make it kind of more scientific, we identify the material properties first. And we used generalized model scattering parameters. And let me just make them visible. Which is covered if you're interested in those publications, and basically it's a spin-off from very old known process based on complex gamma extraction. It's we call it SPP light. This is GMS parameters, and SPP light is just extraction of complex gamma. Ross Speciali used it first in late 60s for kind of different purpose, but here it is used for the material characterization. And material characterization with the separation of conductor and dielectric losses goes like this. First, using lowest frequency, we identify resistivity, but by matching lowest measured insertion loss. We used mechanical calibration kit measurements for this. Then we identified the electric constant by matching phase delay, and identify loss tangent using wideband bimodal. I'll talk about it later. At low frequencies, below 1 gigahertz is usually where you can reliably identify the loss tangent. So it includes the conductor losses during the identification, but roughness losses are negligible at those frequencies. So you can reliably kind of identify it and predict the behavior using causality relationship. Then you identify roughness model parameters matching insertion loss at higher frequencies, usually above 5 gigahertz. And do it for all unique dielectrics, and sometimes it requires some iteration. So alternatively, loss separation process can be done with T-resonator technique. There is publication, there are publications with HP guys on the subject at our website. It's so called in combination with PP light is called gamma T technique. So again, T-resonator is used to identify the loss tangent at about a few hundred megahertz, and then uses in a wideband bimodal, which is causal model, and requires just one measurement point, decay and LT. Has another couple of parameters where the kind of the first lowest pole and the highest pole. This so-called pole continuous model. Usually the lowest pole and highest pole are fixed to very low frequency and very high frequency. So, and if this is done like this, so one measurement point gives you the behavior of the model. So all you see is this results here, decay and LT at one frequency point, 1 gigahertz. But in reality, those are causal models with loss tangent slightly changing over the frequency and grows with the frequency. And dielectric constant basically becomes smaller and smaller with the frequency due to causality requirements, and it's all in the Georgievich-Sarkar model. Also, we use Hurey-Bracken model, which is a causal version of the Hurey-Snowball model. And at the end, the simplest case we did is two roughness models, one for strip, one for microstrip. For microstrip, they use different roughness. So that's why we end up with different model. And core is the same as for all layers, model for the same for all layers, and different models for prepregs, for layers that are expected to be different. So, and in the brackets, you can see the values from manufacturer, and they are not very kind of far from what we ended up, both on dielectric constant and loss tangent. And the only big difference is soda mask value, and this value came from manufacturer of the PC board, so it's probably value tuned into some tool where the improper conformal soda mask model was used. That was our guess, so it's not came from the manufacturer. So note that some manufacturers, some dielectric manufacturers, basically specify now provide some values of DKLT up to 50 gigahertz. But if you take a closer look, those are values taken from few measurements, and just one measurement is enough. And then they use Georgievich-Sarkar model to resample it up to 50 gigahertz to whatever. It can be done even up to higher frequencies. So basically it shows that all that you need is just one point and put it in a Georgievich-Sarkar or wideband Debye model, and that's it. So now let's see how these new models that we came up with, how they close to measured GMS parameters. And right here again, GMS parameters magnitude is plotted on the left, and phase delay is plotted on the right. Measured values are by stars, and circles are models. Models are extrapolating data. You can see how, and in case of inner 3, for instance, we had a resonance in the middle, so the V was not back drilled. Resonance around between 20 and 25 gigahertz, but we were able to extract GMS parameters still with this data up to 25 gigahertz, and the value of the models from inner 2 and inner 3, they are, you can see, very close. So it basically, even with a limited bandwidth, you can expect the model to behave properly at higher frequencies. This is unlike any kind of table-based or multiple Debye models. This is a property of the wideband Debye model, and Hurey-Bracken, obviously, for conductor surface roughness. So what are the compromises here? So if you take a closer look at one of the layers, one of the results for inner 2, for instance, or inner 6 layer, we will see that the model identified like this with just core and prepreg doesn't have much kind of inhomogeneity that observed in real life. In real life, we see that even an odd mode are different, have different phase delay. And so what does it mean? So it means that in reality, you've got fixed, fine crosstalk, and the model will have 0 fine crosstalk, obviously. So, and the only way to deal with this is to introduce some inhomogeneity. You have to introduce a layer of resin rich or glass rich, whatever is filler in those resins, and use another decay for this. So this is one way to deal with this. That will create difference between differential and common, or even in odd modes, and will produce fine crosstalk. We'll see how it correlates at the end. So this is the new kind of the final models identify. Now we have again 2 roughness models, the same roughness models as were before, and 8 dielectric models. In addition to core and prepreg, we have a layer of resin in the middle. This resin, and it has dielectric constant slightly larger in this case. So it means that it's not resin, it's resin with a filler. Most likely. So the alternative is to use the same value for of decay and LT for core and prepreg, and just you end up with just 2 dielectric models per unique layer. So why do we need to do this? Well, technically, when you kind of on a large scale, you will see the analysis to measurement correlation for GMS parameters for each layer is pretty much the same. But when you take a closer look and zoom in, you'll see that even the node modes now are separated. And that produce fixed, and we'll see how fixed correlate next. So I just want to mention that when we did this project, it was manual process in Symbior. Now we have Symbior as decay, where the whole process, including the mode separation, is automated. So basically you have to supply geometry, you have to supply of the cross-section measurements for long and short line, and then Symbior basically gets those data for each unique layer. So before we start looking at the result of validation, I should repeat it that at this point we've got all the data on geometry adjustment, or some data on geometry adjustment. Those are not statistical, but rather some observation on trace width, shape, and back drilling also. The cross sections having some reveal some problems in back drilling. And at this point, we have material models. And we stop adjusting anything. So basically, we take this data and try to simulate the rest of the board without further adjustments. We did it with decompositional approach in Symbior software. So again, those are simplifications. We'll see how far they can get us, like simulating logic separately from connector, and connector models were created from back-to-back measurements because of the connector models provided by manufacturers were far from reality, about 1.5 to ohm far from reality. That's again a surprise. And obviously the first structure we try to validate models with measurements is a structure used for material characterization. So this is long transmission line in layer N6. We've got, and this is a shorter one. Here, using those two, we computed GMS parameters and use those for material characterization. And now let's see how S parameters of the whole thing with the connector correlate with the model constructed in this way. So we can observe relatively good correlation in transmission up to about 30 gigahertz, not so good in reflection. I will explain why. Fixed next correlation is really a kind of good up to 30 gigahertz. And this is in single-ended. And right here we are looking at the differential mode measurements and magnitude. Again, we can see correlation up to 30 gigahertz, and in the phase delay the same thing. So what happened above 30 gigahertz, we'll talk later about it. But you can see also some resonances here. That was a mystery for us at first, but then we just basically figured out what it is, looking at the measurements mostly. So TDR basically explain why we have so much differences in reflection. Reflections are below like 15-20 dB, and you can see about 1 ohm or maybe even more than 1 ohm variation in the impedance. So those are not reflections. So kind of those are actually actual impedance of the transmission line. And why is it so kind of changing so much. We basically don't know. Is it material properties or geometry of those differential lines? What it is, we don't know. So we basically the least informative kind of metric for validating analysis with measurement is eye diagram, often used, but it's easiest to get correlation. You only need correlation and insertion loss, and that's it. But to see the whole picture, you have to see the correlation reflection loss and TDR in basically all S parameters, and then derived from everything derived from S parameters. The TDR here was computed from S parameters also with 15 picosecond rise time from 20 to 80%, just for consistencies, both for from measured data and from simulated data. And obviously in simulation, you don't have those wild variation of the impedance along the transmission line. That's a proof that this is something going on in real structure. So eye diagram is perfect. Another thing we try is to put some BT standard wide strip that can be also used for material characterization by matching the resonances right here. And the fact that measured resonances match the modeled resonances with exactly the same model constructed for differential line, you can see that this is a proof that the model works. So properly accounted for dispersion and separation of the losses. So additional losses from roughness give additional inductance, and losses from dielectric, that's a separate thing. So, and this is de-embedded again also in Symbior data. So on this BT standard, we also observed good correlation in phase delay and in TDR. So it's again looking at all things at the whole picture, you can either figure out the problems or see the deficiencies of software or manufacturer. So some structures here not came out as expected in the manufacturing process. So the reflection, again, this is microstrip structure, more variations, much more variations. So we can see not so good correlation and reflection, very good correlation in facts and next due to proper separation of proper kind of model within homogeneous dielectric. Again, in this is mixed mode, so differential and common. The same thing, good correlation up to 30 gigahertz. And that's TDR again computed with 15 picosecond rise time. You can see much more variation, and so that's expected. So when we did a few cross sections of microstrip, they were slightly different, especially the soda mask kind of flow, and that's a combination of different processes like plating, etching first, plating, and then soda mask, they just pour it on the top. This configuration is not really popular for high-end multi-gigabit signaling, and the reason is it's less predictable. And that you can see why it is less predictable. We don't really have any statistical data. What causes this? That's probably for another investigation, subject for another investigation. But nevertheless, we've got relatively good correlation in eye diagram for the structure. So again, eye diagram is computed from scattering parameters, measured and modeled. So one more structure I'll show, which is differential link with a couple of views. Via back drilling was really measured from the cross sectioning, so it was slightly off. But even with data from manufacturer, we were able to get relatively good correlation. So you can see the whole picture. So this is the key again in validation. On any of those structures we computed after the fact, after the geometry, kind of some geometry elements were adjusted, and after the material unification, we didn't do anything else. And then we looked at the whole picture. This is the key in the process. So often I see kind of, a lot of published results, they are not comparing everything. They are comparing just one thing, like insertion loss. Okay, this is important for kind of eye diagram, but in reality, it's everything is important, and then you have to look at the whole picture. For instance, if you improperly identify the dielectric models, like misplace the losses, commonly you'll see, okay, you get the correlation in phase delay, insertion loss, but then you'll start looking into reflection, into TDR, and you'll see the differences. And that's why we used causal model here for the conductor surface roughness, because of without causal model, with improper placement of the losses, you immediately have some kind of mismatch in all those data. So this is eye diagram. Again, good correlation for this, and not so good for 56 gigabit per second PAM4. And why is it so? So we can see, well, everything is good here. Both signal 28 gigabit per second NRZ and 56 picosecond PAM4, they have theoretically identical spectrum. Kind of first energy in the first kind of loop and the second, but in reality it's with PAM4 differences in the levels and differences in the energy in the first loop and second, that causes it's more sensitive to the problems above 30 gigahertz. So again, we're comparing here measured versus simulated, and remember, simulated didn't correlate well above 30 gigahertz, and so that basically is reflected in this eye. This problem above 30 gigahertz, you cannot get such excellent correlation. So we have to construct model that are good above 30 gigahertz also. There is a complete report available on request, so it's on Google Drive. There is a presentation that shows it, and you can also get all the solutions with measurements and everything, material model unification. And this is a part of the report we put together to show kind of what correlation up to which frequency we achieved. You can see mostly it's 30 gigahertz, sometime lower on reflection. In eye diagram and in impedance, for instance, this structure had something in the middle up to 3 ohm gave difference in impedance of the transmission line. We still don't know this because of it was not cross-section at this particular location. It was supposed to be straight line in there. So in conclusion, I should say that accurate prediction of PCB up to 40-50 gigahertz is really kind of challenging problem. In this project, the correlation was acceptable up to 30 gigahertz, and not for all structures. You can see the complete report if you're wondering which structure were not really correlating well. You have to try before investing in any measurement or equipment or EDA tools. They're all equally expensive nowadays. Cross-sectioning and control of your manufacturer is have to be done to make really kind of things kind of predictable. And obviously material model unification with conductor roughness separation. And by the way, identified dielectric models are really close to what provided by manufacturers. This is basically also a proof that we were sometimes you see in other tools material models going kind of looking really strange and far from the provided manufacturer. Manufacturer use very strict, rigorous processes like Berezkin, like strip line resonator. They are really good techniques, and they the accuracy is really usually good. So in conclusion, I should say that to make predictable interconnects, it requires 2 steps. You have to know geometry adjustment done by your manufacturer. And you have to identify models with separation of dielectric and conductor roughness. And there is one condition, your software has to be validated also. So not all tools are created equal, including electromagnetic ones. Test board or sink or swim validation must be used to basically make sure that everything is expected in every step. And one more thing, use only the structures that you can predict. So if you constructed something that doesn't work, localization break or whatever, just make it simpler and try to make it predictable. And the only one problem with this is to make predictable. In predictability is the localization. So the localization is the key. This is example of platform, validation platform, actually designed with Symbior software. And they are all, some of them are available if you don't want to construct your model. They are constructed differently, not like production boards. So they're more predictable up to higher frequencies, and they use different kind of size for the strips and so on, but that's what it is. So now let's, we are ready for the questions, and I have some. I'll unmute everyone. Let me do this, and I have some questions. And yeah.
Can we unmute individually? Okay, no, it sounds much better. There was a bunch of noise.
Yes, yeah, somebody put some. Yeah, Julia, I've got a question from you.
Yeah, Marco's been answering a few of them, so thanks, Marco. But I wanted to get some additional clarification, if you don't mind.
Okay.
Go ahead.
Marco, are you here?
Yes, I can hear. Yes.
What additional clarification would you like? Actually, it would be good to repeat to everyone. Stack up SL material selection, roughness definitions, and signal launch sensitivity.
Yeah, basically, all of these materials is available on the app note section of the Symbian homepage. When it comes to stack ups, we used 2-ply core and prepreg in order to mitigate fiber weave effect. Roughness definition, well, there is no roughness definition. We just know it's HVLP copper. And again, keep in mind, there's a difference between starting roughness and the fabricated roughness. Because the vendors, they do some micro etching, oxidation, bond treatment. Everyone does it differently. So you have to identify the roughness. And for signal launch sensitivity, well, actually when I was doing the optimization of the launch, I had as a goal to have return loss below minus 20 dB up to 30 gigahertz. But as you have seen, in reality, when we cross-section the launch, everything's offset. So what should be done instead is make the launch so that you don't lose localization. Put the stitching via more closer, and also so that it's not so sensitive for manufacturing variations. The launch on inner tree, that was really lousy launch. We forgot to back drill it. So it had a stub resonance. But still, even with stub resonance at 25 gigahertz, generalized module S parameters, we could extract those up to 22 gigahertz. So as long as your launch is predictable in the sense that it's not, its TDR is not going to differ. So you can even have lousy launches, but as a goal, you should keep them low reflective and not sensitive for the manufacturing variations.
Yeah, the comment you made, Yuri, about the issues past 30 gigahertz to get reliable measurements, is this mainly due to equipment, cables, calibration?
No,
or is this
that's a good question. Before jumping in there, I have few backup slides to show what happened above 30 gigahertz. It's not equipment,
okay.
You'll be surprised, but I have to answer your questions about what was the parameters for the conductor surface roughness characterization. Use SR and SR and RF abbreviations, But
yes.
it comes from unified model where there are two parameters. The first parameter is SR, surface roughness, in micrometers. It's approximately correlates with the RA or SA measurement for the conductor surface. So it's a kind of mechanical peak to valley correlates, I say. So it's not exactly, but correlates. You can use it and fix it as root mean square peak to valley. And second parameter is roughness factor, which characterizes the expected maximal increase in the losses due to the roughness comparing to flat surface. So, and basically, we have converted 6 different models like Hurray, hemispherical, Hammerstadt, modified Hammerstadt, that we basically proposed back a few years ago with you, Chudi, in our paper. Remember modified Hammerstadt? That's the second parameter we added in the modified Hammerstadt. Now we use it for all models, including this Hurray snowball and this Hurray-Bracken causal extension of the model. So those the first parameter you can get even from spreadsheets sometime for just one side, by the way. So that's important. For manufacturer of the foil, for PCB manufacturer, we have nothing. Again, it leaves us in complete uncertainty. So if foil is manufactured rough on both sides and we got parameters for those roughness, then it may be usable models. But in reality, one side is roughened by manufacturer of the foil, another by PCB manufacturer. So, by the way, we can stay and answer a question as long as it takes. So we are not limited and restricted as in any other cases in webinar on the timing here. So we are not going to suddenly leave in 1 minute. No. So, Chudi, was it clear? Or yeah, and I can send you again. I can send you all the kind of description and technical details.
No. This is very clear. I mean, between you and Marco,
yeah, and anyone is welcome to also request all the details. And so, what happened about 30 gigahertz? Actually, this is really interesting. It was a little bit outside of this kind of how to make predictable interconnect. On the other side, it's that's one of the things that were not predictable, not expected. So this is the first measurement Marco did with TDNA. And immediately we notice those notches right here. And again, on 40 gigahertz VNA, the same thing. Same thing on single-ended traces on 40 gigahertz. Then when Marco did measurement with 50 gigahertz, we noticed a couple of resonances. So they look like very kind of similar to fiber wave effect here. So in some cases, people may attribute it to fiber wave. And our first kind of guess was, oh, that's probably fiber wave effect. We started kind of computing how those traces cross the fiber and well, but when we looked at the reflection, that definitely ruled out completely the fiber wave effect, because if we don't have matching kind of reflection, fiber wave effect is a periodic kind of loading of the strip that gives the reflection. So the insertion loss null should correlate with the kind of pole right here with the maximum of the reflection loss, but it didn't. So we even more, this is the reflection was much smaller at the higher frequency right here. So it looked definitely not like a fiber wave effect. And when we looked at the next near-end crosstalk, which means from here to here, infinite crosstalk from here to here, we notice they have maxima at exactly the same location. So basically that's where energy went. And how did it get there? Well, that's how it gets there. So in launch, launch was localized by design up to 30 gigahertz. But at the end, a couple of vias were removed due to manufacturing issues, and that created some gate right here. So even above 30 gigahertz, launch kind of keeps energy inside. But this opening on the side, it creates a path for the energy. And where does it go? It goes into this waveguide created with the stitching vias. So technically, the stitching vias at those high frequencies are must. So you have to stitch all transmission lines along them, strip line, because of those are not kind of the planes in such strip lines have to be maintained equipotential. The only way to do it at high frequencies is to put stitching vias. So stitching vias were placed there, but the distance was a little too large actually for this frequency range up to 50 gigahertz. So basically, you've got cutoff frequency first waveguide at 32 gigahertz and then 29 gigahertz for the second waveguide, this wider one. And the energy propagated between those interplane areas. It's not this one shows power flow density between every single layer in there. You see it like this. It's multi-path propagation. Basically, the energy, in addition to going through the strip line, it goes through interplane area, through all interplane waveguiding structures. That's what happened. So that's and the measurements were excellent. We were able to and at the end, marker basically measured every single structure on the board. A few structures even far apart. You can see right here the energy escapes into interplane area, and guess what? Things have become really coupled at frequencies above probably 40 gigahertz. So we'll see coupling between ports in completely not linked not linked ports. So
Yuri, I guess the question then is: are there any surface mount connectors that are commercially available that do not limit design of a validation board below 30 gigahertz?
Oh, absolutely. Even Marco, go ahead.
Yeah, absolutely, Judy. I mean, you can actually, even with 2.4 millimeter connectors, you can push this forward. The problem was we lost the localization in the via transition, the launch. So you don't have, I mean, that connectors, let's say 2.4 millimeters, they don't have no significant higher order molding up to 50. So you can use those, but the problem is the launch. So one of the lessons learned now is you have to really stitch everything together and look at the signal as a wave. So if there's an opening where it's large enough open, it's going to escape. And also on the board, I measured, for example, traces that were 6 inches away. They were completely on the other sides of the board, and there were plenty of stitching vias across the whole board. At the frequency where we had the launch localization breakdown around 33 gigahertz, you could see a huge increase in coupling. I mean, at some places it was like minus 26 dB of coupling, and these traces are 15 centimeters far away. So you get signals traveling across these parallel plate cavity. So if you do any antenna design or so, this can ruin your day. So launch localization is really important. I mean, localization in general. I mean, every time. Also, I put some structures, for example, single-head vias, where you don't have any return vias nearby. Those things resonate. They start, there's a lot of ringing going on. So if you want to build predictable interconnects, it's very important. Only build structures that you can accurately simulate. So, and it discounts, I mean, the boundary conditions you put in your 3D field solver, it has to really mimic what happens on the board. So if you use perfectly electric conducting walls, so you have no energy escaping the box. Then, well, you have to stitch really plenty of stitching vias, so you have a closed cavity there. So localization is a really important fact.
In your conversations with your PCB vendors, it sounds like the one that worked on this board was a pretty decent one. Have they stated any limitations to the amount of stitching vias you can place around the signal via, or any sort of manufacturing tolerances to keep in mind when you're trying to create this localization?
Well, I mean, when it comes to stitching vias, no, you can place, and they have some manufacturing guidelines, for example, how close vias can be placed together. But basically, I mean, when I did the simulations of the launch, well, again, the result is dependent on which boundary conditions you use. If you use that there's no leakage outside this air box, well, then you don't see these resonances, but they happen there. So you have to really design your interconnects in such a way that you can accurately simulate them. Mm-hmm. And also, I mean, just from these lessons learned with inner tree, that one that has stub resonance, I mean, even if it's really lousy launch, it was around 32 ohms, and it was designed to be 50. Plus it had a resonance. Even with this resonance, we were able to accurately extract GMS parameter. So just keep them localized. That's totally better.
After the localization breaks, and everything becomes problematic. You cannot
unpredictable, exactly. Then you have to simulate the whole board. Yeah.
So yes, you end up with simulation, and this is valid for VIA design. This is not just for the launch design. Again, this is valid for VIAs, for single-ended specifically. It's not over-designed. So if you want to see what does it take to get your launch kind of localized up to 60 gigahertz, there is a demo video in demo video section on the launch where I use this launch and another one designed by Scott McMorrow for one of our validation boards with Molex, which walked up to 60 gigahertz. So it was slightly kind of 1.8 millimeter probably connector from Molex, but the launch, you can see how kind of I don't remember that, but it was about 16 vias around the launch in there to make it work, make it localizable up to 60 gigahertz, and that's and again then make it work up to 60 gigahertz strip line. You have to put the stitching much closer to this, and if necessary, take into account the effect of those stitching vias, because of the essentially you have to think about those traces, not about like, okay, connections, this thing is connected with this one, but rather as waveguiding structures again. So you have to prohibit launching these waves in the layers where they are not supposed to be, and this localization of launch and transition. And then you have to take care of the energy that goes along the traces should not escape anywhere else. So that those stitching vias have to be kind of very close. Sometimes I get questions, well, on those boards you've got this, all the layers are ground, they're stitched together and everything. Again, it's not realistic. In reality, you have ground signal, power signal ground, or something like this. And I usually answer, just forget about it. So if you want predictability and you want your interconnects work as expected, just use ground signal ground and stitching just at this location, and moreover stitch it along the transmission line. And that ensures and you saw how important it, even for PAM4 56 gigabit per second. So,
and also I can add that, for example, in the launch, because the layout engineer, he actually not all planes are stitched together. There are some of them are VCC. So you have antipads, and actually in between those layers,
in the middle right here.
Yeah. So there you have also most of the leakage, because the impedance of the cavity increases with the distance between the reference planes.
Mm-hmm.
So you can inject more noise into the parallel plate cavity. So yeah, I mean, in the end, we can say about this predictable interconnects, you have it really comes close with the decomposition analysis. You have to be able to simulate each block in isolation, because otherwise it's computationally prohibitive to simulate the whole link. Let's say if you have a 15 inches long trace and you want to do everything in 3D solid rate, it's not possible. You're going to run into numerical problems. It's not going to converge. So you have to rely on decomposition analysis, and in order for that to be valid, you have to be able to really simulate all the discontinuities in isolation. So localization basically means everything in this case.
Mm-hmm. Mm-hmm.
So that's basically my mantra now is that you have to use and design only the structures you can reliably predict. And some people assume that they can easily predict strip line behavior without even stitching vias or anything like this. That used to be true, but if you move into this kind of microwave and millimeter wave domain, this that becomes completely different picture. So you have to establish your structures that you can really kind of predict, and the validation boards is a kind of tool to be able to see what is actually what can be done in this domain and how to keep it predictable. So some structures on this board, this particular board, like AC coupling capacitors, were less predictable. So we found out that those were difficult to predict, and came up with a different kind of approach how to construct this AC coupling structure to make it more predictable. So,
yeah. And actually, we have in the full report one of the structures. It was a single-ended via where the return via was far away. That one lost localization already at around 4 gigahertz or so. So, especially, I mean, vias, those are really nasty things at high frequencies. Especially if you have through-hole vias, they can inject noise in between every cavity. And we have seen on this board, this noise spreads really far away. It doesn't get damped. I mean,
you said 4 gigahertz, Marco?
Well, it depends. I mean, if you don't localize your vias, you're going to inject noise at even lower frequencies. So, especially even if you have, for differential vias, you have some localization between the P and N in the via. But if you have a common mode signals, like you have due to skew or some asymmetry, and then that can mode convert and end up as a differential noise. So vias, yeah, if you please provide the return paths really close to them. That's the best. Otherwise, you're gonna run into problems.
Yeah, 16 vias per launch sounds like horror story, but that's why, yeah, if you want, some of you do want 112 gigabit per second PAM4. So that's kind of that's a millimeter wave. The simulation has to correlate to measurements up to 80-something gigahertz. Think about it.
Mm-hmm.
That's quite a challenge. I don't know. That will require some rethinking about how to make the PCB interconnect. So if somebody just insists that they used to do it like this, like power signal ground, or use just one stitching via per some number of signal vias, they will not. They are not going to survive in this. So that's and the sooner you get into this kind of thinking, let's try to see what we can reliably predict. And the predictability is basically you're not losing the energy from your channel, and all your energy propagates as you expected. That's it. That's one thing, just to start with. And the second thing already, yet another is what are going to be losses, and who's going to control it, how are we going to control it. So far, no kind of mechanisms to do this. So we kind of, three of us discussing thing, but do anyone else has questions? Okay.
Yeah, I can just add, Yuri, on the discussion that you have brought up.
Yeah,
especially
absolutely.
we have seen for 28 gigabaud signals. So you have a null at 28 gigahertz. So depending if you use NRZ or PAM4, we had this resonance at 33 gigahertz. So according to all these rules of thumbs, well, it shouldn't matter. It's way beyond 14 gigahertz. We have the Nyquist. Well, it's different. This reasoning, I think now when PAM4 is finally coming out, we're gonna see some issues. We cannot just extend this reasoning we had for NRZ to PAM4 without paying the price. So we have to go really have much more control higher up in the frequency.
Yes.
I think you're absolutely right. You know, part of my part of the reason I'm asking some of these questions and trying to get a better understanding is, you know, it becomes more and more clear to me that we have to distinguish between what are some of the drivers for this, right? There was a lot of resonant activity that you noticed in the S parameters that you initially thought was fiber weave effect. And now, Yuri, if you didn't have some of the experience and some of the work we've done in the past to look at return loss and not find identical points of the same resonance, you know, some people will conclude that is FWE, right? So it's important to really distinguish between what's really driving some of this misbehavior. Is it the fiber weave? Is it additional attenuation because we don't have the correct roughness modeled? Is it a limitation of geometry because of manufacturing tolerances or just the design of the launch in general? So at the higher and higher data rates, right, just like you said, Marco, at 28 gigabits per second, it's important for designers to really be able to distinguish between all the different drivers and then start to look at them, like you said, in isolation to see if improvements can be made, right? So I guess another question I have, and maybe this is outside of this forum, but do you have a follow-up to this investigation, Yuri and Marco? I haven't been following things for quite a while, but do you guys have something in the next year or so, DesignCon, if you will?
Well, Yuri has had some interesting papers gonna present, but basically,
Mark, you can tell that you got EVR2 in the production almost.
Yeah, I mean, what we want to, because EVR1, well, it was a lessons learned board. We learned a lot.
It was forensic signal integrity kind of experiment.
It is actually. It was lots that we learned. For EVRE2, well, we have to extend the launch localization frequency. We have to push beyond 50 gigahertz. And also, what is interesting, for example, is to make a study where, let's say you have on the same board, let's say use blind vias, so you have upper part of the stack up, you use HVLP copper, and then on the lower part of the stack up, you use RTF copper, just to see that we are once for all maybe settle this question: what is losses due to surface roughness and what is losses due to the dielectric? That would be really interesting.
We were not able to basically find a manufacturer who is doing the completely flat copper, just to really kind of same technology, flat copper and same technology. Maybe Chudi, you can do this rough copper, and just to show that proper loss separation works. So, for instance, for flat copper, I don't expect the additional kind of losses and additional inductance due to roughness. And so the latest kind of trend that this HVLP, VLP copper, it gives you additional inductance. That's what captured by Hurey-Bracken model due to kind of currents flowing in the in relatively weird way. And there is a demo video on how they actually, on our website, how they actually flow. But and I hope that this EVR2 project will be done sometime this next year. No, we are not presenting it at DesignCon because of it's a kind of project in process. At DesignCon, there's going to be another very interesting kind of investigation report that we do with some other company, with Intel actually. I can mention because of that. That's going to be public domain. And they're trying to do some statistical investigation. Remember those variations on TDR? Where do they come from? Is it material or is it geometry? And that's what we'll try to answer. So we are kind of in the middle of the project now. But that's going to be really interesting to see. I'm wondering what it is, and everybody asks, well, what it is. Maybe you know, I don't know, but to answer this, you need really kind of
you need a lot of data. You need a lot of data.
A lot of data, yes, a lot of work done. That's why we did this automation for the material characterization with separation of dielectric. So because of there are going to be kind of hundreds of files processed, measured, and they already did it, and then they do automatic kind of cross-sectioning and to put it together with the material characterization. That's where that should is supposed to give out more kind of data, and then goal is actually construct some realistic models that include the statistical variations. And so far, no data from PCB manufacturers. No, probably they have it, and but they don't share it, and it's not really statistical.
Yeah, and part of it is data collection for PCB vendors. It's sort of related to what they understand very well. If they understand particular process tolerance very well, then their data collection is very good. If they don't really understand it, then the data collection is not very organized, right? They don't set parameters as to what they're measuring and how it's repeatable and so on. But I think they're getting there. I think some of these investigations help them understand a little bit better what the SI world is looking for them to capture consistently and in the right formats. Anyway, I think I've taken up plenty of your time for this conversation.
Okay, that was great discussion after the presentation, and I would like to thank everyone for participating and listening to us. And feel free to contact us if you need access to those data or more extended presentation. And thank you very much.
And also, you can just add for the end, Shudi. You have to really work closely with your PCB manufacturer. For example, if you are talking about control of the etch process, it has to really do with how much copper fill you have on that particular layer, for example. Same thing with if you want to predict what will be the press thickness of the layers. So you have to really have this iterative contact with the PCB manufacturer, and I mean, a chain is not strongest than its weakest link. So yeah, all these parts needs to be joined together and have an open discussion about the limitations and learn from each other, because these guys they know a lot. Yeah,
I agree completely, Marco. I'm sorry, I don't think we met before. I've done a lot of work with Yuri in the past, but I've spent a big part of my career working with, both at a PCB vendor and also in the material world. I'm sure you and I will have a lot more conversations in the future. But that's kind of where I've lived for, you know, a greater part of my career is on the material side. But yes, I completely agree with you. There's a lot of things that that's why your microstrip was so was so messed up, because of the plating that they used just to get the coverage on there. So anyway, it was a pleasure to talk to you. It's the first time we've
we will continue offline. Okay.
Sounds good. Thank you.
Thank you very much, everyone, and goodbye.
Goodbye.
Bye bye.